let's talk about vapor pressure. What is vapor pressure? And why do we care? Well, vapor pressure, what do we mean by it? Vapor pressure is the pressure of the vapor. Helpful, right? But what do we really mean by this? What do we mean by the term vapor, and what is the difference between a vapor and a gas? You probably have never really thought about the fact that there is technically a difference between a vapor and a gas. A vapor is a term that's used to describe a substance that is in the gas phase if gas is not the most stable form of that species or that compound at that temperature and pressure. What the heck does that even mean? It means like this. It means looking at water in the gas phase at 1 atmosphere and 25 degrees Celsius versus 1 atmosphere and 200 degrees Celsius. We expect H2O to be in the gas phase once it reaches 200 degrees Celsius. Absolutely. The boiling point of water is 100 degrees C at 1 atmosphere. We'll talk about that as well, how we find these and what do we mean by boiling point. But we can all agree that at 100 degrees Celsius and 1 atmosphere, water should boil. So exactly at 100 degrees, we have reached an equilibrium. Water will either boil or condense. If we get above 100 degrees, we expect water to be in the gas phase. But then why do we have water in the gas phase at 25 degrees C? We know we do. If I take a glass of water and I spill it and I don't clean it up, it will eventually evaporate away, right? That spot will not always stay wet. It will not stay wet until it reaches 100 degrees and the water can boil away. I could spill it at 25 degrees C and it will eventually evaporate away. Why will water evaporate? I can spill it at 85 degrees Celsius and it's going to go away faster. It's still going to go away before it reaches its boiling point. And so when I'm doing that, when water's escaping into the gas phase before reaching its boiling point, it's actually called a vapor. So I want to give you a thought experiment here. Basically what we have here is a box, and it's a sealed off box, a vacuated box that I place one single ice cube in. So my water is in my solid phase. I'm going to slowly increase the temperature on this and over time allow it to warm up until it reaches room temperature. Let's assume room temperature is 25 degrees C. So I've slowly warmed this up and allowed it to reach room temperature. In that time, the ice cube has now melted because we've passed the melting point of water, which is, 0 degrees Celsius, 1 atmosphere is when water will melt. But if I was to actually examine the box, what I would have in this box would be water in the liquid phase and water in the gas phase. So the little pink dots here are supposed to represent water in the gas phase, whereas this is your water in your liquid phase. Well, why do I have both? I haven't reached 100 degrees Celsius yet. And again, this is because water has a vapor pressure. The vapor pressure is defined as the pressure exerted by a vapor in equilibrium with its liquid or solid state. And it's known as a dynamic equilibrium. So what equilibrium is a concept we haven't covered quite yet. It'll come soon enough, but an equilibrium is what's happening here. Okay, so let's look a little bit closer into here. What a dynamic equilibrium means is that what's happening is some of these water molecules that are in the liquid phase are escaping and going into the gas phase. The rate at which these are escaping is the same rate at which the gas molecules are condensing back down into the liquid phase. So if I examine the system, again, dynamic equilibrium is what it's called. And that means as the gas particles go to the liquid phase at the same rate, I see liquid molecules going to the gas phase. So from a bird's eye view, if I looked overall to the box, the amount of liquid and the amount of gas is staying constant. But the particles themselves are changing phase. Some of those liquid molecules are escaping to the gas phase. Some of the gas molecules are condensing back down to the liquid phase. So again, what is vapor pressure? Gas molecules exert pressure. We learned about that in the gas chapter, right? PV equals nRT. If something is in the gas phase, it is exerting a pressure. So vapor pressure is the pressure that these water molecules are exerting on this liquid phase below it. In this case, in the liquid phase, it could also be happening between gas particles and their solid phase as something sublimates instead. But vapor pressure, the pressure of those particles that are in the gas phase and how they're pushing back down on the liquid that remains. So the stronger the IMFs, the lower the vapor pressure. Why? If I have really strong IMFs, it's harder for the molecules to escape. Does that mean they will never escape? No. Water has fairly strong IMFs, but water still has a vapor pressure, okay? But it just means the stronger they are, the lower the vapor pressure will be, the less molecules that will be able to escape into the vapor phase. For a given liquid, the vapor pressure increases with temperature. This goes back to what we talked about when we talked about viscosity. If I increase the temperature of the system, the particles have more energy, they're able to move more, they don't rely on each other as much to find their energy minimums, they don't need those IMFs as much, and the particles are just moving faster, so they don't have as much time to form attractive forces to other molecules. So the vapor pressure will increase as I increase the temperature, because as I increase the temperature, the particles are moving more, and they're more likely to be able to escape into the vapor phase. That's why if I spill water at 25 degrees C, and I spill the exact same amount of water at 85 degrees C, the water at 85 degrees C will dry before the water at 25. A liquid is considered volatile if it has a vapor pressure. It is easily vaporized. So here's a new term for you, volatile, okay? Volatility means that this molecule escapes easily into the vapor phase. Things that you smell are volatile. Air fresheners, candles have volatile components to them. Perfumes and colognes, you spray them on you and then you can smell them, right? You're smelling those particles. You sprayed on a liquid and all of a sudden you're smelling something in the gas phase. Those are volatile compounds. So a liquid is considered volatile if it has a vapor pressure, meaning it's easily vaporized. If it goes into the vapor phase pretty easily, it is volatile. So the more volatile is something that has a higher vapor pressure, is something that has weaker IMFs. The stronger the IMFs, the less volatile, right? Because stronger IMFs mean it's holding into the vapor phase. Stronger IMFs means it's harder to escape to the vapor phase. It's holding into its condensed phase, which is your solid or liquid phases. Condensed means, solid or liquid, we have a fixed volume, possible fixed shape. Therefore, it's less volatile. So for example, let's look at diethyl ether versus ethylene glycol. Diethyl ether is very volatile. Ethylene glycol, not very volatile. If I looked at diethyl ether, I can boil this with my hand. It has a boiling point of 35 degrees C. If I look at ethylene glycol, it has a boiling point of 197 degrees Celsius. Why? Well, let's draw them out, see if we can figure it out that way. If I look at diethyl ether, diethyl ether means that I have CH3, CH2, CH2, CH3. Or drawn out, I'm going to draw out the Lewis structure, not the Vesper shape, but I'll talk about it in just a sec. I've got a methyl group here. I've got a CH2. Got an oxygen trapped in the middle. CH2, and then the methyl group on the end. Every molecule shown here. Every carbon, the oxygen, all of these are sp3 hybridized. The carbons are all tetrahedral. The oxygen, because it has 2 lone pairs on it, is bent. So if you actually looked at the Vesper shape of this, it is a bent molecule. However, what I want you to think about, okay, so you got oxygen, and you're like, okay, cool, well, I've got a bent structure. That's great, but these guys are pretty big. So these side groups are taking up a lot of space, right? Their electron clouds are there. They're just taking up a lot of space. So although this is a polar molecule, these side groups are pretty big, and I probably drew them too small. Probably, big electron densities to them. Oops. And they're kind of blocking how much that oxygen can really do. So although it is polar, it has pretty weak dipole-dipole. And I see its boiling point represent that at 35 degrees Celsius. Again, I can hold this in my hand and boil it. So 35 degrees C, it's higher than water, but 35 degrees Celsius to get into the gas phase is not very high. That is body temperature. If I then look at the ethylene glycol, let's try that one down here. General Lewis structure here. Again, all the carbons and the oxygens are sp3 hybridized here. Everything has 3 areas of electron density. If I looked at the carbons, they are still tetrahedral. Both oxygens still bent. The difference here is that I have hydrogens attached to those oxygens. So whereas before I couldn't do that, now I've got this group going on. Now I've got that hydrogen bonding. Not only that, it's on the outside of the molecule. So even though carbon, the CH2 groups in the middle aren't the smallest thing in the world, because they're not, these take up actual space, I've still got that hydrogen bonding on the outside of the molecule and on both sides. It is completely symmetrical. So I see that it's not very volatile because I've got hydrogen bonding going on. And I see that come through on its properties. Not very volatile with 197 degrees Celsius boiling point for ethylene glycol versus very volatile, easily vaporized with the boiling point at 35 degrees C. So how does this all come about? This all comes about from boiling point. And we're going to talk about the definition of boiling point in just a sec. But when I look at this, 760 torr, remember what 760 torr means? This is the same as 1 atmosphere, okay? And I just talked to you guys about diethyl ether, and I see here I've got a line, and I apologize, I drew these before I had an iPad on the computer, so they're not the best lines, but I think you get the point. When I look at the diethyl ether line here, I've got the line here, and it's intersecting this line at 35 degrees C. I just told you that was the boiling point. I've got ethylene glycol's line here, and I see the vapor pressure increasing, intersecting this line at 197 degrees C, okay? And again, what I'm talking about here is the vapor pressure of the system versus the temperature. I look at water in the middle here, and I'm like, okay, I've got water, vapor pressure's increasing, and it's intersecting at 100 degrees C. And if I look at the last one, ethanol here, I can see that it's, intersecting at 35 degrees C. Definitely a pattern here, right? What I'm seeing is that when the vapor pressure of the system equals the atmospheric pressure, I'm reaching the boiling point. So to the left of this line, the system exists as a liquid. To the right of this line, it exists as a gas. There's some kind of connection here between vapor pressure and atmospheric pressure. And that brings in our definitions of boiling point. Boiling point itself is defined as the temperature at which the vapor pressure of a liquid equals the external pressure. Your external pressure is your atmospheric pressure. Why? Because that's the pressure that's external, right? The atmospheric pressure is pressure around us. Normal boiling point is defined as the temperature at which the vapor pressure of a liquid equals 760 torr. Why do we have to have a normal boiling point? Well, because we don't all live in the same atmosphere, right? We live on Earth. But we don't all live in the same comparison to sea level. Some of us live in lower ground, some of us live in higher ground. Throughout the world, we have different places. And so we have to have something so that I here in North Texas can talk to someone who lives in Denver, Colorado, and be able to compare our results. So normal boiling point is our standard. When I say water boils at 100 degrees Celsius, that's at 760 torr. That is if I'm at exactly 760 torr. Now here in North Texas, we are close to 1 atmosphere, usually a little bit below it. Instead of 760 torr, we're usually around 750 torr, 755, 745, somewhere in there. And you can just look up the barometric pressure. That's what it is. If you look up barometric pressure, it's represented for us in inches of mercury, which you guys should be able to convert easily with your the conversion factors But that's where this comes from, the normal boiling point, because we have to have a standardization. So with that in mind, it shouldn't surprise you that the stronger the IMFs, the higher the boiling point. We've already talked about that a little bit, right? Also, the stronger the IMFs, the higher the melting point. One thing I want you guys to think about that most students know but don't actively think about is that melting points and freezing points are the same point. A melting and freezing point is the temperature in which a solid and liquid are in equilibrium. So if I have water at 0 degrees C, it is in equilibrium between the liquid and solid phase. If I go above 0, it's going to melt. If I go below 0, it's going to freeze. But at 0, I have reached an equilibrium. So water melts and freezes at the same temperature. The same with the boiling point. Water vaporizes and condenses at the same temperature. What does all this mean? Well, let's look at some different values here. We've got boiling points of water at several locations of varied altitudes. And I see here I've got Mount Everest in Tibet, the highest mountain peak on Earth, elevation of 29,035 feet. The approximate pressure in atmospheres is only 0.32, and water is boiling at 78 degrees Celsius. Mount McKinley in Denali, Alaska, highest mountain peak in North America. Okay, 20,000 feet elevation, so, a little less than 10,000 less than Mount Everest. We've got a vapor pressure of 0.46, and water's boiling at 83 degrees C. Okay, California, 15,000.6 atmosphere at 87 degrees Celsius. Denver, Colorado, 5,300 feet, 0.83 atmospheres, and water's boiling at 94 degrees C. In Boston, Massachusetts, which is truly at sea level, 20 feet elevation, 1 atmosphere, 100 degrees Celsius. So what I see is when I'm closer and closer to actual sea level, I get closer and closer to actual value of 1 atmosphere for pressure, and the boiling point is increasing for water. The lower the external pressure, the lower the boiling point of the liquid. The higher the external pressure, the higher boiling point of the liquid. And it's kind of a funny application here. This is how your pressure cookers work. Pressure cookers work by increasing the pressure of the system so that water boils at a higher temperature, but what it's doing is it's cooking your food faster because it's giving your food higher temperature to cook. And so pressure cookers work by giving it that, increasing the pressure, increases the boiling point of water. So when the water is boiling, there's more heat, so your food cooks faster. And of all things, this is how KFC really got started so fast and so successfully is Colonel Sanders came along and figured out to use pressure cookers to cook chicken in a fast food setting. It hadn't been done. No one else was doing it at that point. And he came along and used pressure cookers to cook the chicken. He was able to cook it really, really fast in a fast food setting, output a lot of chicken really fast and cooked, and made, lots of money that way just by taking advantage of a pressure cooker. That's all your pressure cooker is doing is it's just taking the sample you already have and giving it, making it higher pressure. Therefore, the boiling point of the water is higher. And when the boiling point is higher, that means there's more heat to cook your food faster.